Hello, you WebLogic app vulnerability. This is the third one in the web cache deception series, and it's a practitioner lab called Exploiting Origin Server Normalization for Web Cache Deception. If you've watched the first two, you already have most of what you need. If you haven't, don't panic. I'll build the ideas back up as we go, and there'll be a card up in the corner to the Delimiter video if you want the deeper version of 1-bit. Before we open anything, let me get the core ideas straight, because the name is scarier than the bug. Web cache deception is basically this. You trick the cache into saving a private page. A cache is just a middleman that sits between you and the real server and keeps copies of things that don't change much, so it can hand them back fast without bothering the server every time. Images, style sheets, JavaScript, that kind of thing. The whole point of the attack is to get the cache to treat somebody's private logged-in page as if it were one of those boring static files. Save a copy, and then we walk up and grab the copy. There are 3 things you need for this specific lab, and I'll re-explain each one when we actually hit it, so treat this as just the map. First, hit versus miss. When a response comes back from the cache's own saved copy, that's a hit. When the cache doesn't have a copy and has to go ask the real server, that's a miss. And a lot of these labs are kind enough to tell you which one happened in a response header called x-cache. Dude, x-cache is such a cool superhero name. Am I a genius? You'll see x-cache miss the first time, and if the thing got cached, x-cache hit the second time you ask. Watching that value flip from miss to hit is how we know caching is even happening. Second, a static directory rule. Caches are often set up with a lazy rule, like anything under this one folder counts as static, so cache all of it. So if the rule is on a folder called resources, then anything with /resources at the front of the path gets saved. No questions asked. Hold on to that one. Third, and this is the actual bug, normalization. Normalization is just a server tidying up a messy URL into a clean one. Things like decoding encoded characters and resolving those ... steps that mean go up a folder. The vulnerability shows up when the real server and the cache tidy up differently. In this lab, the real server resolves that stuff and the cache doesn't, and that little disagreement is the whole exploit. One last piece before we start, because it trips people up. When we do path traversal, we'd normally write ... to climb up a directory. Problem is, our own browser is helpful and resolves ... before the request ever leaves the machine, so the cache never even sees it. To stop that, we encode the slash by hand and write it as %2f, but you're going to see it anyways during the walkthrough. The browser leaves %2f alone, so our ... survives all the way to the server. So anytime you see ... %2f in this video, that's just an up one folder step that we've disguised so the browser doesn't eat it. Okay, let's go.
Okay, let's go.
The goal is to find Carlos's API key, and we've got the usual Wiener Peter account to test with. The lab also gives us a list of possible delimiter characters, the same kind of list we used in the previous video. We will actually use it briefly here as well, before moving on to the normalization part of the lab. Let me access the lab. I've got Burp Suite Community running in the background, and I'm in a normal browser with FoxyProxy switched on, so my traffic is routed through Burp. The lab hands me an account, so let me log in. Wiener as the username, Peter as the password. And there's my account page. It says my username is Wiener, and right under it, my API key. That's the kind of thing we're hunting, a page that shows you private information. Now the lab's real goal isn't my key, it's Carlos's key, another user I can't log in as. So the plan, eventually, is to get Carlos's account page saved into the cache and then read it. Let me flip over to Burp, into Proxy, HTTP history, and find the request that loaded that page. There it is, get my account, right-click, send to repeater. That's where all the poking happens from here. First thing I want to know is whether this page is even cached. Let me send it as is and read the response headers. And, no x-cache header at all. No miss, no hit. There's a cache control header sitting there, but that only says the page could be cacheable. It doesn't mean anyone's caching it. So right now the account page itself is not being cached, which makes sense, it's private. If you're coming off the last video, your instinct is to throw the delimiter trick at it straight away. I did. It comes back looking totally normal, no cache header, nothing, which is the lab politely telling you this one is different and you can put that toy away. Okay, so before I reach for the real bug, let me quickly rule out the two easier shapes this could have been, because that's the honest way to land on the actual one. Shape 1, path mapping. The question is whether the server is loose about extra junk on the end of the path. So let me change the path to my dash account /abc and send it. 404, not found. So the server does not just shrug off an extra segment. It actually goes looking for /my-account/abc, doesn't find it, and errors. That kills the path mapping approach. While I'm here, the other easy shape is a rule on file extensions. Cache anything ending in .js or .css. Let me tack a fake extension on and see if it suddenly gets cached. Nope, no cache header, still nothing. So there's no extension rule waiting for us either. Two doors closed, which is fine. It means we're headed somewhere more interesting. That leaves delimiters, and this is the bit the last video was about. So here's the short version. A delimiter is just a character a server treats as end of the path, cut here. The classic one is the question mark, which starts the query string. But different frameworks quietly treat other characters as cut here too. A semicolon, a dot, all sorts. If I can find a character the real server treats as a cut, but the cache doesn't, that's a discrepancy I can pry open. Discrepancy. What a beautiful word. So let me test a whole pile of characters at once. First, a clean base. I'll change the path to /my-account abc. No slash this time, just the letters stuck straight on. Send it. 404, good. That's my reference for a broken path. Now right-click, send to Intruder. In Intruder, I want to slot each candidate character into one exact spot between my account and that ABC. So clear the auto-selected positions, if there are any. Click right between the N of account and the A of ABC and add a payload marker there. Attack type stays sniper, one position, one list. Then in the payloads panel, I paste in the delimiter list. The lab literally gives you one on its start page. So let's go to the list. Copy it. Paste it in there. Good job, El Nino. And this next bit matters. Down under payload encoding, there's a checkbox. URL encode these characters, and I turn it off. If I leave it on, Burp encodes my semicolons and slashes into percent codes, and then I'm testing the encoded version instead of the raw character, which is not what I want. Off it goes. And let's start our attack. Peekaboo. When it's done, I sort the results by status code, and here's the payoff. Out of that entire pile of characters, exactly one comes back 200 instead of 404. And, it's the question mark. And the response even has my API key in it, which honestly is a little anticlimactic. We brute force the whole character set to discover that the one delimiter the server respects is, the single most ordinary punctuation mark on the internet. And that's actually the problem. The question mark is universal. Literally everything treats it as the start of the query string, the cache included. So there's no disagreement there to exploit. Both sides read it the same way. Dead end, but a useful one, because it tells me the delimiter route is closed, and the real bug has to be in normalization, which is, conveniently, the name of the lab. Real quick ad break. When I started CyberSec, the hardest part was that everything was scattered all over the place, so I pulled it into one library, 33 modules, foundations through SOC and Blue Team. It is on my Etsy, link in the description. So let me test that directly. I want to know if the real server does normalization. Does it decode encoded characters and resolve those ... steps? The clean way to check is to hand it a path that only works if it tidies it up. Back in repeater, let me clear off that ABC and build this. /AAA/... %2f my dash account. Oh, you don't need the slash there. Reading it out, a made-up folder called AAA, then an up1 folder step, the dot dot with the encoded slash, then my account. If the server takes that literally, character for character, it should error, there is no folder called AAA. But if the server decodes that %2f back into a slash and then resolves the dot dot, the AAA and the going up cancel each other out, and it lands right back on slash my account. Send it. Oh, 200. And there's my API key. So the server absolutely normalizes. It decoded the slash, walked up out of the fake folder, and served me the account page. That's half of our discrepancy nailed down. The origin server, the real backend, resolves this stuff. Now I need the other half. I need somewhere the cache is caching, but where the cache does not do that same tidying up. Let me go back to proxy HTTP history and actually look at what is getting cached on this site. Turn the filter off for this one, and there's a pattern. All the genuinely static stuff, the images, the JavaScript, the SVGs, they all sit under one folder, /resources. And if I click one of those and read its response, there's the Xcache header we've been missing everywhere else. So the caching lives under /resources. Let me confirm that properly. I'll grab one real file. /resources/js/tracking.js and send it to repeater. Send it once, Xcache miss, the cache didn't have it, it went and fetched it. Send the exact same thing again, and now Xcache hit. It saved my first response and served me the copy. That flip, miss then hit, is caching, confirmed and on tape. Now the real question. Does the cache normalize like the origin does, or not? Let me poison the path a little. I'll take that tracking file and jam a %2f right after the resources prefix. So it reads /resources/%2f, then the file. Think about what a tidy cache would do. Decode and resolve that, walk up out of resources, and now the resources prefix is gone, so the resources rule wouldn't apply, and it wouldn't cache. Send it. 404, sure, but look at the header. X-cache miss. Send it again. X-cache hit. So even though the path is nonsense and the file doesn't exist, the cache still cached it, which means the cache is not resolving that dot dot. It's reading the path literally, seeing /resources at the front and going, that's in my resources folder, I'll cache it. That's the sloppy behavior I was hoping for, a cache that reads the raw path and doesn't clean it up. Let me just prove that's a real folder rule and not some fluke. I'll strip it down to /resources/abc total garbage, a folder, and a made-up name. Send it. 404. Xcache miss. Send it again. Xcache hit. So there it is. The cache will save anything, and I mean anything, as long as /resources is at the front. It just cached a 404 that points at a file that has never existed. It doesn't even look at what the page is, it just sees that prefix and files it away. And that's both halves of it right there. I've got a real server that resolves %2f and a cache that saves anything starting with /resources and refuses to resolve %2f. Those two facts are about to collide. So let me build the payload that uses both. I'll go back to that repeater tab where I had /AAA/%2f my account and just swap the fake AAA folder for the real one, resources. Here's the trick, told from both sides. The cache looks at /resources/%2f my account and does not tidy it up. It just sees /resources at the front, decides it's a static resource, and gets ready to cache whatever comes back. The real server looks at the exact same string, decodes the %2f into a slash, resolves the dot dot, climbs up out of resources, and lands on /my-account, so it happily builds the private account page. Same URL, read two completely different ways. The server generates the secret, and the cache, thinking it's a style sheet or something, files it away. Let me send it, you little pancake-handed goblin. 200. My API key is in the response, and the header says x-cache miss. Send it again. x-cache hit. So my own account page just got saved into the cache. The mechanism works. If I stopped here, I'd only be robbing myself, which is not much of a heist, but the machinery is proven. It's time for our new superhero, x-cache, to remind you to hit like, subscribe, and leave some stupid comment below. Thanks, lil bud. Back to the vid. Now to turn this on Carlos. There's one wrinkle I have to handle first. I just cached this URL with my own session, so the cache is now holding my account page under that exact key. If I send Carlos to that same URL, the cache already has a copy, and it'll just hand him mine, and nothing new gets stored. So I need a fresh key nobody's touched. Easiest way? Add a throwaway query string on the end. Something like $WCD. That changes the cache key, which means the cache treats it as a brand new request it has never seen. So when Carlos loads it, the cache has no copy, it's forced to go ask the real server, and the real server, seeing Carlos's session, builds Carlos's account page, and that is what gets cached. Then I come along and read that same key. So let me head to the exploit server. This is the part of the lab that plays the attacker's website, the page we're pretending to lure Carlos onto. In the body, I'll drop a tiny script that, the moment Carlos's browser loads the page, throws him at our crafted URL. I already explained this script in our previous videos. You have to insert your own lab ID there, so just go there and copy it from your URL. Paste it there. So this is our cache buster. I will explain now what happens, because after we deliver this to the victim, Carlos, we only have 30 seconds to act, since if you remember, that's the time the cache is stored. Behind the scenes, Carlos's browser opens that link, hits our URL, the cache has never seen the WCD key, so it misses, and asks the real server. The server hands back Carlos's private account page, and the cache saves it under our key. His secret is now sitting in the shared cache with our name on it, so to speak. So let's store it. Then, deliver exploit to victim. Now I just go collect it. Let me load that same URL in my browser. And there's the My Account page, but read it. The username is Carlos, and that's Carlos's API key, not mine. The cache handed me his stored response. Sorry I put in the API key to the Solution tab without recording, but I have faith in you. You can copy-paste this key alone, hehe. So let me put the why back together, because the individual steps go by fast. The bug was one small disagreement. The real server tidies up a messy path decoding %2f into a slash and resolving ... to climb up a folder. And the cache doesn't tidy at all. It just reads the raw path and caches anything that starts with /resources. We proved the server tidies up with /a////% 2 fmyaccount, coming back with the key. We showed the cache caches by prefix and ignores the ... by watching a pure garbage /resources path flip from miss to hit. And then we aimed one URL at both flaws at once, /resources, so the cache would store it, ... %2f my-account, so the server would read it as the private page. A cache buster made sure we captured Carlos's copy and not our own. And the second his browser loaded our link, his API key got parked in the cache for us to walk off with. That's the pattern for the whole normalization family, honestly. Find where the cache and the server clean up paths differently, then write one path that both of them read the way you need. That's the third lab in the series done. Good work getting through. I'll see you in the next one. Maybe. Like, comment, sub.